We're going to use diagrams to explore logical relationships between categorical statements. And I want to start by just explaining how the diagrams work. Let's compare and contrast two kinds of diagrams that you shouldn't confuse. You've probably seen a diagram like this before. This is called an Euler diagram. Leonhard Euler was an 18th century mathematician who explored various uses for this type of diagram. It depicts established relationships between sets. What I mean is, we know that the set of whales is a subset of the set of mammals, even though we don't have lists for both sets, and this relationship is drawn into the diagram from the start. Don't just think of this picture as some sort of metaphor for grammar. I think it's a good idea to imagine that all the whales are somehow obligated to hang around inside that little circle, and likewise for the mammals, so that the whales are then fulfilling two obligations by being where they are. Now, suppose we want to draw in the set of all creatures that live underwater. Where would that circle go? Here's an acceptable way to draw it. The shape also encloses all the whales, because they live underwater. And there are some other mammals that live underwater, like dolphins and so on. Then there's an area allocated to underwater dwellers that are not mammals, and mammals that don't live underwater. Now, if we want to draw in a set of creatures that are not mammals and don't live underwater, like birds, it would be in a separate region of the diagram. That's all I want to say about Euler diagrams. They aren't the kind of diagrams we are mostly interested in anyway. I mention them only because they feel pretty natural, and sometimes students confuse them with the kind of diagram that suits our needs better, the Venn diagram. Venn diagrams are named after John Venn, the 19th century mathematician and logician who explored their potential. Whereas Euler diagrams depict established relationships between sets, Venn diagrams depict potential relationships between sets of unknown membership. That's why they're more useful for exploring deductive logical relationships, wherein we assume the premises of an argument to be true even if they're not, and then we ask whether we can get to the conclusion with no additional information. A Venn diagram begins from a state of no information. So for a given number of sets, it always starts out looking the same way, no matter what the sets are. If we're only talking about one set, it looks like this. Pretty simple. At this point, it doesn't look much different from an Euler diagram. But the areas in the diagram represent different things. This is supposed to be a set whose membership we know nothing about. It could even be empty. And let's not forget, the outside of the diagram represents a set 2, the complement of our set, and we don't assume any knowledge about the complement either. It too could be empty, which would mean our set contains the entire universe of discourse. Let me make this more concrete by bringing up a set whose membership is actually unknown. We don't know if the set of ghosts has any members, or if you do know, you can pretend you don't. So the diagram so far could represent the set of all ghosts. Essentially, the diagram just divides the universe of potential set members into two parts. One part designated for the ghosts, and the other part, outside the circle, designated for anything that's not a ghost. You'll definitely have to pretend you don't know if there are any objects that are not ghosts. Now suppose we want a Venn diagram for two sets, again, both of unknown membership. We need to draw another circle partially overlapping with this circle. The orientation is traditionally left to right as I have them here, although that isn't essential. Since we declared the first set is a set of all ghosts, let's come up with something concrete for this other set to be as well. How about mermaids? We're not sure whether there are any mermaids, or we can pretend we're not. This diagram divides the universe of potential set members into 4 parts. Let's start with region 2. It's actually easiest. Region 2 represents the intersection of our two sets. That is G intersection M. I'm going to be a bit pedantic for a second here about exactly how you describe this, because there are a couple of things people commonly say that are not quite right, or at the very least likely to get you thinking in less helpful terms about it. This region represents things that belong to both sets. Ghosts that are also mermaids, if there are any such things. In order to be hanging around in this region, a mermaid has to die and become a ghost to haunt it. Sometimes people say, isn't it ghosts and mermaids that belong here? And I worry about whether they have the right idea. Any individual member of this intersection has to be a ghost and a mermaid. But if you mean there's a bunch of ghosts and then there's a bunch of mermaids running around in here separately, that's wrong. Then there are also people who cling to one particular use of Venn diagrams that they were taught when they were kids. They say, isn't the middle similarities and the outside parts are differences? That's not right either. If our two sets were things about ghosts and things about mermaids, then yes, the intersection of things about ghosts and things about mermaids is the set of similarities between ghosts and mermaids. But that's not what we're talking about here. The members of these sets are the actual ghosts and mermaids themselves, if there are any. To make it more concrete, suppose it were the set of males and the set of college instructors. Now I'm a member of both those sets, so I would belong in region 2. But I'm not a similarity between males and college instructors. What would that even mean? I'm a male college instructor. Now, let's return to our sets of unknown membership, ghosts and mermaids, and the other regions of the diagram. What about region 1? What belongs in region 1? I hope you didn't say something like, just ghosts. Both region 1 and region 2 have ghosts. There are two questions that need to be answered about any object from our universe of discourse before we can say it belongs in any of these regions. The questions are, is it a ghost and is it a mermaid? So region 1 contains only the ghosts that are specifically not mermaids. That means it's the set you get if you take the set of all ghosts and remove any of them that are also mermaids. Does that sound familiar? It's the difference, G minus M. Meanwhile, region 3 represents M minus G. In other words, mermaids that are not ghosts. And then we have the region outside any of the circles, region 4. Things belong here if they are neither ghosts nor mermaids. We don't have words for such things collectively, other than to say, rather artificially, they are non-ghost, non-mermaids. Remember that, just like the Venn diagram for one set, this diagram so far contains no information about the membership of any of these sets, subsets, intersections, and so on. Any of these regions could still be empty. One way to think of it is that it's like we're providing boxes for potential set members to go into, once we know what they are, how our universe of discourse is populated. And once we find them, we'll ask two yes-no questions about each and every member of the universe. Is it a ghost? And is it a mermaid? And then we'll know which box to put it in. Now in the next video, I'll explain how to represent the information provided by standard categorical statements on a diagram like this.